The next speaker is Philip Kaddaj, and his talk is on Chernavsky's theorem about the union of codimension 1 cells. Please.
But in English, yes, or in Russian, or
Yes, I think it should be in English.
I don't understand
the title.
Oh my! What is the verb?
The union.
The
Union.
union. Oh,
Of codimension.
Sorry. I will. Most of the things I write, I will speak out loud. So hopefully, if my writing is not understandable, at least my speech will be. Yeah. So I guess I'll just start with a brief sort of review of some similar things to what Olga was saying. That cells and spheres in Rn can look very different, and so here are some few examples of some one-dimensional cells in R3. So there's a PL, smooth, and wild cell, and so the last example of a wild cell, that's the Fox R10 cell, which is so Olga had the sphere version. So if you thicken this, take a tubular neighborhood of this and take its boundary, you get the sphere that was in Olga's pictures. So I'll start. So I'll recap with some definitions, which I think were already mentioned in the previous talk, but I'll just run through them again. So a sphere or a cell in Rn is flat if there's an ambient homeomorphism, i.e. a homeomorphism of pairs that takes the embedded sphere into the standard version of the sphere. And similarly, a locally flat if there's a homeomorphism of pairs of an open neighborhood, and the open neighborhood intersect the sphere. So usually we have some picture like this, and this could be our sphere S, and here it can look something like this. And then there's a homeomorphism which makes it look standard. Okay, and I'll start with some history and motivation which led up to some developments in this field. So initially there was the Schoenflies conjecture, and this has different formulations. I think one of those is still open at the moment in the smooth case for n is equal to 4. But so the topological version was solved in first by Maser and first by Brown. So the version that I'm going to state is the following: a sphere in Rn is flat if it is locally flat at all of its points. Sometimes this is stated in terms of the sphere admitting a bicolor. I'm using a result that a sphere is locally flat. A sphere that is locally flat everywhere admits a bicolor. So yes, so this was proved by Maser and Brown independently, and completely different techniques. So Brown used some propositions and some properties of cellular sets, and Maser used an infinite connected sum. So this theorem was then strengthened by Cantrell, which says that actually if we don't consider any n, but we restrict ourselves to considering n greater or equal to 4, then there are no a sphere that is locally flat from a set E. The set E cannot contain any singularities. So the first example that I was talking about, this wild arc, and this picture that appeared in the previous talk. So this is precisely a counterexample to the case n is equal to 3. So we have a two-sphere that is wild that fails to be locally flat at one discrete point, and there's no ambient homeomorphisms of the sphere, which flattens it. But the claim is that if we pick a dimension higher, n is equal to 4 or higher, then we can always straighten out these discrete singularities. And so this was a result by Cantrell, and it was later generalized by Chernavsky, who showed that the union of two flat n cells, n-1 cells in Rn, such that their boundary is also a flat n-2 cell, then their union is flat. So initially, so a quick aside, the actual initial theorem was proven not just for n-1 cells, but for k cells, as long as k is not equal to 2. And I will discuss the case of codimension 2 separately a bit later. But so his proof used engulfing, this is Starling's engulfing lemma, and so it was only valid for n is equal to 5, and it was later improved to n is equal to 4 using cyclic covers. Around the same time, so Kirby announced the same result, so the union of two cells, two flat cells is flat, without using engulfing, but using some results of Latcher. And then in 2006, a new paper was published, which stated the following theorem, that if we have an embedding of an n-1 ball into Rn, that is restricts to be flat on both semidisks. So by semidisc, I mean the intersection of the ball with the upper half plane or lower half plane in Rn. Then Q is flat. So I'll quickly discuss why. First of all, why is this a generalization of Cantrell's theorem? Okay, so suppose we know some version of the Kirby-Chernavsky result. That is to say, the union of two n-1 balls is flat. Then we can isolate the singularity. So suppose we have some embedding of an n-1 dimensional manifold into an n-dimensional manifold that has a singularity at a point, i.e. there's neighborhood of this point where the embedding is locally flat everywhere apart from this point P. Well, then we can isolate the singularity in the ball and cut this ball in half along P into some balls B- and B+ such that P lies on their boundary. And so Kirby then used the result of Latcher, which states that singularities can't exist on the boundaries of K cells for K sufficiently big. Another way of seeing this, and I think this was discussed previously in the seminar, was that arcs in Rn for n greater or equal to 4 don't have any discrete singularities. So I'll explain this very briefly. So how to see this? So this key lemma, which says that arcs with discrete singularities are usually PL modulo 1 point. They're a union of points and segments, a countable union of points and segments. And so the lemma can be rephrased in the following manner: an arc in Rn for n greater or equal to 4, that is a union of points and segments, is flat. And the idea is the following. So first we will construct, so I'll take the limiting case, n is equal to 4, and all the arguments can be reproduced like for arbitrary, for n greater or equal to 4 as well. So first we construct a homeomorphism of R4 to R4, which takes the arc to some subspace, three-dimensional subspace, homeomorphically. And then we straighten it out using the Klee trick. So the Klee trick says that if we have two embeddings of some compact manifold C, then we can take the product of these embeddings, which is suppose alpha goes into Rn and beta goes into Rk, then their product is defined just alpha of x, beta of x, and that's an embedding of C into Rn plus K. Then these embeddings are equivalent by ambient homeomorphisms to alpha times 0 and 0 times beta.
Excuse me, he will explain me in Russia. Я просто не понял строчки. Верхней. Объединение точек. Что такое?
Прямых объединение, вот, ну, тут имеется в виду, что дуга в РН, которая полиэдральная, кроме одной точки, она плоская.
Дуга А, которая есть объединение точек и сегментов.
Да, счетное количество точек и сегментов.
То есть прямых. Понятно.
Ну вот чего-то такое, например.
Вот так. Дуга в РН больше 4.
Да.
Ну, это понятно, да.
No, but
Excuse me.
in R3 this is false, right?
Yes. For example, this is a counterexample. Ну, это можно нарисовать по-другому, чтобы все было.
Какой пример случается?
Yeah. Okay. Yes. So, is this obvious? Should I continue on this?
Maybe not.
Okay. Right. So essentially we get the moral is this, the Chernavsky Kirby theorems. Sorry?
So we are now proving this lemma about a countable union of
no. So I think we have proved this before. I proved this in a previous talk, but I was just running through the idea very quickly. And the two main ideas. One is to construct a homeomorphism R4 to R4 such that it takes A into some three-dimensional subspace, and then we apply the Klee trick. So we have an arc lying in some three-dimensional space subset of R4, and then we can straighten it out into we can find a homeomorphism which makes it flat in R4, not in R3 but in R4. And this homeomorphism is the idea is we find a family of lines. These lines are going to be perpendicular to the hyperplane, such that they intersect this arc in exactly one point. And the homeomorphism is going to be defined as just we send points of this arc, the intersections of. So suppose we have some line which intersects A only in one point, and then we will send all of these eventually into these hyperplane via homeomorphism. And such lines exist, for example, because we can take, so if A we write as a union of AN, and then we can take sets CMN, which are all possible lines, segments between AM and AN. And this is a closed affine subspace of Rn, and their countable union cannot cover it. So such lines must exist.
It's an idea to prove Klee lemma.
Yes, just the Klee lemma. Okay. So I said I would discuss the case K is equal to of codimension 2 separately. So it turns out that actually we do not have an analogous result for the case of codimension 2. And a counterexample is by Sasinsky. And essentially, he wrote some article on generalizing connected sum of knots for if we don't just consider the standard models of knots as S1 into S3, but Sn-2 into Sn. And analogously, one can define connected sum of knots as like by drawing. So here's the case n is equal to 3. We draw on knots in cylinders, and we make sure that they intersect the cylinders in disks of the correct dimension. So if like they're all going to intersect in disks of codimension 2, and then we stack these cylinders such that we have identity along the disks. And if we want an infinite connected sum, we're allowed to draw, instead of drawing our picture in the cylinders, we take a cone, and we draw these things in some infinite cone tending to some point P. And one can show that, so this is actually a very similar idea to what was used in Mazur's proof of the Schoenflies problem. And with the connected sum operations, the set of knots form a commutative monoid, one quick note I would like to say is that these embeddings of these things, which we'll call knots, they are locally flat. I do not I don't know if people have thought about this, but I don't. For me personally, it didn't make sense to consider this for just arbitrary embeddings of Sn-2, since this connected sum depends on a disk, on some disks on the embedding, and if the embeddings can be like pathological, it's not clear why this connected sum is well defined. But so these are all locally flat. Okay, and so Sasinsky says, proved the following, that there exists some knots such that this infinite connected sum fails to be flat, but is the union of two flat disks intersecting in a flat disk. And in fact, in the same paper, his previous theorem was that if you take any knots, any locally flat knots, and you do this construction of infinite connected sum, you'll always get something that's not locally flat. You'll always get something that's not flat at this point P. This point P will always contain a singularity. Okay, so which particular knots admit this? So what are the criteria on these knots? So he calls this canonical cut. So this is a picture of some knot in one of the cylinders, and this statement can be made precise, but essentially what he means is that we can cut this sphere into two disks, and each disk we can flatten each disk within the cylinder hi plus 1, and there's quite a lot of knots for which this is possible, and the example that he gives is knots that are obtained by spinning. So what do I mean by spinning? So I'll draw like the three-dimensional version. So if I have suppose I had a point in R3, and then I could that lies in some half plane R2 plus. Then I can rotate this half plane around some axis which lies in R3, and this point would sweep out a circle. And so this construction is exactly analogous to this, but just with knots. And instead of rotating around some line, we rotate around a two-dimensional plane in R4, or something of codimension too in Rn. And so yes, so I actually had a question, because for me it seemed that this canonical cut pretty much always happens, and so Sosinsky's did not discuss whether there are some knots that don't admit these canonical cuts. So I was wondering whether anyone was experienced with these already and knew certain constructions which don't admit canonical cuts. If not, then I can just move on. But essentially, what will happen in the limit is that we take all of these knots, and we have, and each of these individual knots can be made as the union of two flat disks, and the entire union is going to be a flat disk which contains a singularity on its boundary. But as we know, then this is still flat, but their union is not flat. Okay. So I feel a bit nervous about speaking about the proof in front of the author, considering I haven't had that long as well to read about this. But I don't know if people want to hear about this. I will do my best to explain, and please feel free to interrupt me if I'm saying something totally wrong. Okay, so so the idea is there's two constructions that are used, and a sequence of 5 lemmas. And so first I'll introduce some notation. So we're going to look at Rn as Rn minus 2 cross R cross R. So here's a picture. I'm going to denote pi alpha, the half planes homeomorphic to Rn minus 1, which have boundary Rn minus 2 and make angle alpha with some prescribed plane, which I will call pi 0. And then for each point x in Rn minus 2, I can consider the plane orthogonal, the two-dimensional plane that's orthogonal to this, and I will denote this by px. And usually we draw, like in what follows, I will draw all my pictures within px, and then we will sort of glue them together as x varies along Rn minus 2. Okay. So the first construction is this thing called a fence. It's a way of separating a closed set and a pi alpha. So supposed M is a closed set. There's some extra conditions on M. For example, locally it lies on this, but it's not too important. We construct a fence by taking so within this px we have coordinate circles, right? And these circles can vary as I vary their radius, and we can choose arcs on these circles such that they lie on one side of pi alpha but do not intersect M. So this is a picture of what is happening. And then the endpoints of these circles sweep out a surface. And this surface is called a fence. Okay, the next thing, which is probably even more important than the fence, is this arcwise homeomorphism. So the statement is the following: is that if we have four closed sets A, B, C, D, such that either one of them is a fence or a pi alpha, and that all intersect in Bn minus 2. So I'd like to remind that this whole direction is Rn minus 2. So all of these intersect in, for example, in Bn minus 2. Then there's a homeomorphism which maps B to C in some neighborhood, and is in some larger neighborhood is identity. And this homeomorphism is constructed it's quite nothing very difficult. We just take this segment and we map it to this segment, and similarly we take this segment and we map it to the segment here. And then it's quite easy to reduce it to the identity like on a larger neighborhood. Okay, so then essentially we can rewrite theorem 1. Theorem 1 is that if Q is flat on both semidisks, then it's totally flat. Okay, so I'll rewrite. So there's a theorem. The rewritten version is the following. So suppose there's some homeomorphism Rn which takes oh, I forgot to say, when I say Q of alpha beta is going to be the region between these planes. So I take the union of all these. So suppose we have some homeomorphism such that a h of q of minus pi by 8 gets sent to h of q minus pi by 8. Then the claim is that bn minus 1 union h of bn minus 1 is flat. Now, why does this imply our first theorem? So suppose suppose we have this is our initial.
Yeah, so it looks like we're a little bit lost. Yes.
Okay. Should I continue? Okay. This is maybe some pictures will help. The point is that okay. The point is the following. So when we first embed Q, we have no idea what it looks like. We can flatten it on one half, so you can make Bn minus 1 flat, and then we lose control of the other part. Now, using the arcwise homeomorphism, firstly we can construct fences that are arbitrarily close to this Bn minus 1. And we can send these fences to, for example, the planes pi by 8 and pi minus pi by 8. And then we regain some more control. And we would like to show that and we would like to show that this is flat. And essentially this is what the theorem states. And so the idea is how to prove this is the following: is we will construct a sequence. So at each stage we construct a homeomorphism pi, which is the same as h on bn minus 1 plus, but that the union bn minus 1 minus and pi of bn minus 1 plus is flat. So again, our initial homeomorphism, we don't really know what it does to each pi alpha, and so we can apply it so that it squeezes everything, so that q of minus pi by 8 to pi by 8 gets squeezed in between these planes. And then so Chernavsky then constructed a four-sheeted covering, which makes the following true, where qi are just rotations of this by 90 degrees. So this is q0, q1, q2, q3. There's a definition which he uses, which basically tells us when things are arbitrarily, when a plane embedding of pi alpha is arbitrarily close to pi beta. The idea is to get to keep iterating on homeomorphisms until we get in a situation where the image of pi alpha touches pi alpha for a very large number of alpha, namely, for example, alpha between minus pi by 2 and pi by 2. And in this case, we can show that what we get is flat. And this is the first lemma in the paper. And so the idea is to keep applying the arcwise homeomorphism in order to get pi alpha to touch its image. So once we have, this first condition allows us to get touching in for one plane. So the image of one plane will touch pi alpha. Then using a four-sheeted covering, we can get pi alpha to touch its image 4 times for 4 values of alpha. And once we have 4 values, we can generate from 4 values of touching, we can generate a 5th, and then we can generate a 6th without altering the previous touching values. And this is his third lemma. And so in effect, what we have is, if I know that my embedding maps pi alpha to something that touches pi alpha in 4 values, I can then construct a countable sequence I can modify this embedding such that for a countable subset, the image of pi alpha will touch pi alpha. And this is just done successively. If I have 4, I can get a 5th without affecting touching in the previous values. And then if I have a 5th, I can get a 6th without affecting the previous touching values, and so on. And the last observation to note is that if pi alpha touches its image for a dense subset, then pi alpha touches for all alpha, i.e. in the closure of this dense subset. And so one particular dense subset that we can consider is some like base 2 rationals, for example. And then we make sure that we number them A0 to AN and so on. And we have a way of getting it. If we know that it touches for 4 of them, then we can get it to touch for the next. And then we can get it to touch for the next and so on. And so we can get it to touch for this whole set. And so we can get it to touch for everywhere. And if we can get it to touch for everywhere, then we can flatten it. Yes. I think that's all I had to say. I was a bit nervous about presenting this. If it's okay, I don't know. I personally didn't fully understand certain details of this proof. So when reading, I tried to come up with my own, and I sort of tried the elementary thing, and there's a few problems. So I don't know, while the author is in the audience, maybe you've tried something similar yourself and then chose not to do this. Would it be okay if I asked some questions by explaining what I thought perhaps would be an argument, and where it could have gone wrong, and whether you think that there is no remedy, or whether you think that there is some hope.
Philippe, that would be nice, I think, but we also have a problem with time.
Oh, sorry. Okay, then yeah, of course.
So may I suggest that and I think, well, I had difficulty to follow what you were saying. Well, that could be my problem, because I had to be distracted in the beginning, and then I got lost. Maybe everybody else followed, but anyhow, I would suggest that maybe you could tell us this and your questions once again in a more slow way. And if Alexey Viktorovich agrees to listen, that would be very good, I think. Еще раз послушаем клип более спокойно, но не сегодня уже.
Да послушаю, то, что вы написали. Я очень обещать не могу, просто можно, я прочитать могу. А насчет того, чтобы приехать, это мне...
Нет, ну по Zoom, по Zoom можно подключить.
По Zoom, может быть, хорошо. Ладно, сообразили. Вот.
Because I don't know, my idea is very simple.
Разобрался, но вот насчет конечных about finite cover, I would like to remark that it was firstly idea of Zibelman in this theorems about curvature and so on. Not on this theme, but he has used this kind of. So it would be good to mark it. If it's published, or is it published?
No.
No. But it would be published.
I don't know. No, this was.
If so, then mention the.
Okay.
Finite cover is the idea of in this question.
What's the reference?
But certainly, I wanted to regard this proof. It is interesting to me what is new here. So I don't know, possibly we make a person conference on
Another meeting on the seminar, yes?
Possibly if you will have a text of this proof, that will also please set to
So, Philippe.
now I can say nothing essential, but I would like to consider this more detailed.
Philippe, maybe you can send some text to Alexei, yes?
Okay, yeah. Yeah, sure. I'll do that. Yeah, it needs to be written up a bit better. I have some text, but it's not written up very well.
Yes.
So if it's okay, I would ask you to maybe wait until I can write it up a little bit better, and then I'll send it.
By email, you may find in this
Yes.
announcement. Yes.
Okay.
Okay, so let's send Philippe for his talk. Are there
Чуть было написано Александр Мегас.
other questions? Okay, if no other questions, let's thank the speaker again.
А мы с вами туда повернуты своими затылками.
Да, так получается.